Hello everyone, welcome to this wind power engineering webinar, wind turbine reliability, the importance of highly reliable pitch control and blade sensing systems. I'm Paul Dvorak, editor of Wind Power Engineering magazine. And let's see, before we get started, I want you to know you can be following us on 3 of the social medias, windpowerengineering.com, and we'll have a couple questions at the end. And if you wish to tweet on this, you can do so with #tag wind reliability. Joining me today are Nick Harper. He's Moog's application manager for blade sensing systems, and Steve Black. He's Moog's senior business development manager for its components group. Pitch control and blade sensing are 2 great topics, so let me first tell you a little bit about our speakers, and we'll turn the microphone over to them. Nick Harper is Moog's application manager for blade sensing systems. He has extensive knowledge with the optical strain monitoring in many areas of wind turbines all over the world. Nick has worked closely with major turbine manufacturers in developing methods appropriate for factory installations and for operational units on wind farms. The past 2 winters, Nick has been actively involved in commissioning a variety of rotor monitoring systems, including ice detection systems for turbine manufacturers and operators. Then we have Steve Black. He's a senior business development manager at Moog. He has over 20 years experience in design and development of slip rings for industrial applications. Steve works directly with the wind turbine operators who are looking for improvements and cost savings. He's located at the Moog Components Group in Blacksburg, Virginia. All right, Nick, you're up first.
Okay, Paul, thanks for that. I think I've got it. So before we start, what I want to mention first is that Moog's ice detection system is part of a rotor monitoring system, Moog's rotor monitoring system, which we call our RMS system. This is a system designed specifically for wind turbines. It enables operators to monitor wind turbine performance, rotor imbalance, blade damage, ice detection, which is the subject of this slideshow. It uses sensors which are mounted at the root of the blade. These optical sensors are totally immune to lightning and to EMI effects, electromagnetic induction effects. Looking at slide numbered 5, we're looking at wind turbine installations in North America. This slide shows the current capacity of wind turbine installations in North America, but more interestingly, for the purpose of today's talk, it shows the proportion of installations that exist in cold areas. Approximately 65% of wind turbines installed in North America are in geographical areas that inter-average below 20 degrees Fahrenheit. These are perfect conditions for the formation of ice. Looking at the next slide, entitled Traditional Ice Detection. Traditional ice detection currently normally uses meteorological equipment. This equipment does not detect the buildup of ice on blades. It simply measures icing conditions. Therefore, it doesn't give the operator very good warning, and it gives the operator very much time to allow him to take the necessary action to perform shutdown to his turbine. The problems we have with ice is that ice build-up on blades can give rise to ice throw. This is a hazard, a special hazard near populated areas, and also causes additional drivetrain loads, which are often in excess of design loads. And these might cause out-of-balance loads on the turbine shaft, which in turn can cause damage or premature damage to the gearbox. For this reason, many turbines are prematurely shut down whenever there's a risk of ice buildup, and often not restarted until visual inspection confirms the absence of ice. This is particularly difficult in remote locations or at night in foggy conditions, which leads to unnecessary high loss of revenue. In the next slide, the ice detection solution, if you look at the left-hand side, you can see that the system works in 2 ways. On the left-hand side, we see that the system is working under operational conditions. In other words, the turbine is rotating. Look carefully at the blade, which has the blue dot at the root of the blade. This is the typical location of one of the optical sensors. The sensor here is measuring the bending moment of the blade as it's rotating. This generates what effectively is a sinusoidal wave pattern. As the ice builds up on the blade, shown by the blue line down the leading edge of the ice, this effectively alters the amplitude of that signal. As the amplitude increases above a predetermined threshold, the turbine will be shut down. So that's the dynamic case. On the right-hand side of that slide, we can see what we refer to as the static case. So the turbine is now closed down, it's now stopped, but it's still operating. The system is still detecting. What it's doing now, instead of measuring as it was previously in the time domain, the system is now working in what we call the frequency domain. What we're relying on here is the background wind, the characteristic background wind at the wind farm. Normally, it can be as low as 3 meters a second and the system still performs. We use that to excitate the natural resonant frequency of the blade. This natural resonant frequency, as we know as engineers, as the mass builds up due to the ice accreting on the surface of the blade, as it builds up, it changes the mass of the blade, thus reducing the natural frequency. Looking at the next slide, we can clearly show the build-up of ice correlated with the data. If you look at the right-hand side of the slide, you can see this is for a period from October to approximately the end of December. For the first 70 days, you can see that there was no ice build-up. After about 72 days, there was ice started to build up on the blade, as shown by the picture showing moderate ice conditions. At approximately day 78, you can see that was a significant amount of ice. After day 78, you can see that it returned back down to the zero ice condition again, and at that point it would be safe to restart the turbine. The next slide shows a comparison of two turbines at the same wind farm. We have turbine A and turbine B. Both turbines are normally at the same altitude. Notice the strong correlation of data from the two turbines. In this case, you will observe that there is an inherent noise level of about 100 and 150 kilograms. This is significantly reduced for providing blade pitch information. So if we can pick up the blade pitch information from the turbine, we can reduce that noise level. But however, even without that blade pitch information, you can see quite clearly from this slide the differences that both the turbines, turbine A and turbine B, correlated very well with the same amount of data on the same day. If we look more closely at that data, if you look at time at about 40 days, look carefully and you will notice that turbine A had ice for about half the time that turbine B did. Now this would imply that the operator was able to start turbine A about 2 days earlier than turbine B. This of course would give a better increase in revenue, return on revenue for that particular turbine. Right, in this slide, this looks a little bit busy at first. We're looking here at a comparison between turbine rotating in dynamically at first, which is the blue information, and then on the right-hand side we have the turbine which is stopped. So let's first look at the blue data. As you notice, the turbine at day 2 was rotating with no ice condition, but slowly over a period of a day and a half maybe, the blue information is slowly going up, showing that the turbine is now building up ice on the blades. At some point, the threshold, which is decided between moving sensors and the operator, this threshold will be exceeded, and at that point the turbine will be stopped. If we look then at the red information, this is the turbine now static, but the system is still providing useful data. Look how the data still increases the mass still increases on the blade. It goes up for another 2 days. Ice is slowly building up on the blade over another 2 days. After about day 5, the data becomes flat again. And then after day 6, you notice how it reverts back to the 0 condition. So this shows very clearly that the system works, operates very well when the turbine is rotating, providing useful data, but more importantly, more useful from the operator, it's also working when the turbine is stationary. Let's look at the next slide, which shows the essential features of the turbine. You notice, of the monitoring system, I should have said, notice that at the root of each blade, we have 4 independent fiber optic sensor arrays. These sensors are installed at the cardinal position of the blade. That's the leading edge, the trailing edge, the pressure surface, and the suction surface. The sensors are very rugged and very well protected, so they will last for the length of the lifetime of the blade. The sensors in turn are connected to the interrogator unit. The interrogator unit we call our ENV, or our environmental chamber unit, and that's mounted in the hub of the turbine. It can be also mounted in the root of the blade or mounted in the spinner. It doesn't really matter, but the point is it's mounted in the rotating part of the turbine. The data then in turn needs to get back out of the rotating part of the turbine, and there are various ways of doing that. The first way, well, one way I mean, would be to use a GPRS modem. This enables the operator to send the data back to his plant or his factory, or in some instances we have the data sent back to us here in the UK for subsequent analysis. Another way is to send the data via slip rings back into the nacelle. And at that stage it can be connected to the customer's SCADA system for direct control of the turbine. So as the ice builds up over a certain level, the SCADA system can effectively control the turbine, close the turbine down if necessary. Looking at the final slide, slide 12, we can see the various components of the monitoring system. As I mentioned previously, we have the optical sensors installed at the root of the blades. These in turn connect to the interrogator unit in the hub. If you look at the picture in the bottom left-hand corner, you can see the interrogator mounted in this particular instance in the root of the blade. Next to that is the wireless system which connects the system to the hub. The sensors themselves are shown over on the right-hand side of that slide on the green patch, as we call it, and that contains the optical fiber. The optical fiber has been wrapped up in this small piece of composite, which makes it very robust for subsequent handling. If you look at the picture at the bottom right-hand of that slide, you can see a photograph taken from inside the blade where we're looking at the sensors, 2 of the sensors mounted possibly at the pressure surface and at the leading edge of the blade. So, looking at the final slide, what are the benefits of Moog's ice detection system? The ice detection system can provide information to enable operators to shut down the turbine automatically, and it's only done when the ice loads are in danger of exceeding the specification or present a real danger of ice throw. The ice detection system is able to measure when ice has been shed, enabling generation to restart earlier and therefore with confidence. The system typically delivers about $15,000 US per year in terms of increased revenue. The other main feature I want to mention is that, remember, this system is part of the RMS system, as I mentioned previously. So using the same sensing system, additional software features supplied by Moog can interrogate the information and deduce from that such information associated with blade damage and rotor imbalance. This can, and possibly will, further reduce the overall payback period of the system. The ice detection solution can be implemented on any kind of utility scale wind turbine. We have this system installed on many turbines all over the world, and so far we have not yet received one sensor failure. In September 2009, the system was certified by Germanischer Lloyd. And of course, it's fully supported by the Moog Global Organization. And that, ladies and gentlemen, concludes what I want to say about ice detection systems today.
Thank you very much, Nick. That was very good and informative. And now I'd like to pass the microphone over to Steve Black. Steve, you take the microphone now, and the screen is yours.
All right, thank you, Paul. Appreciate the opportunity to talk to you today about Moog's pitch control slip ring solutions. First of all, to set the stage, the critical nature of the slip rings in the pitch control application is the slip ring is mounted in the back end of the cell, but it's at the end of the gearbox, most typically if there's a gearbox, or directly in the center of the generator if it's a direct drive system. The slip ring is responsible for conducting everything that's happening out in the hub, everything that's rotating, the controls, all the power requirements out in the hub. Also could be involved with the rotor monitoring solutions that Nick just talked about. But the slip ring is needed in the turbine to be able to transfer everything that's rotating in the hub back to the stationary portion of the control system. So as you can see, it is quite an important part of the operating system. So what are the big challenges for the turbine owners and operators? What are they looking for in pitch control slip rings? First of all, life. You need to maximize the life in the pitch control slip rings, as they do in everything in the turbine, to try to reduce the requirements for technician time in the turbines and to keep the turbines up operating and producing power. The environment is obviously a major concern with the operation of the pitch slip ring, and again, as well as everything in the turbine itself. As Nick pointed out, you have a large population in the United States and North America with turbines operating in cold weather, and of course that is replicated around the world in Northern Europe and in other locations as well, where you have operations in very cold temperatures. Then the other extreme of that is where you have operations, say, in the southwestern part of the United States and even down into South America, where you have turbines that are operating in sometimes very humid environments and very hot locations. The increasing of installations offshore is certainly going to be a major environmental challenge for everything in the turbine, slip rings included, with the precious metal contacts or the contacting surfaces that are there, and even just installations that are near shore, near coastal areas. The salt air environment itself provides some unique challenges for the slip ring. The electrical systems need to be extremely robust. These slip rings are handling everything from high power, which is starting to inch up into the hundreds of amps as you get into blade de-icing, much larger blades, much larger control systems, requiring more power to servo motors. Plus, you need to have a unit that's very capable of handling very low-level signals and communication protocols. And of course, maintenance. In an ideal world, there would not be maintenance required in a turbine. Of course, we all know that's not the case. Turbines do require a significant amount of maintenance, but the key is to, where possible in components, to reduce the requirements for maintenance, to take that out of the equation or reduce it as much as possible. And of course, it all comes down to reliability. The reliability of a device, how long it can last, how well it performs, becomes absolutely key to the owners and operators. In that rotary interface I spoke about a few minutes ago, there are, of course, several different types of devices used. Today we're talking primarily about the electronic slip ring solutions, which is the predominant method used to transfer the power and signals at that interface. But also, of course, there are hydraulic solutions out there. Hydraulic systems which use hydraulic actuation to move and pitch the blades are almost always used in conjunction with a slip ring that is used for some low level of power and, of course, the signal and position feedback information. So you have the electro-hydraulic systems that are out there as well. One of the items of growing interest in turbine operation is fiber optic slip ring solutions, where we're actually pointing the fibers at one another and transferring the fiber signal across that rotating interface, using multiplexers to put different varieties of data and information across a single fiber. There's also dual channel fiber joints to use for redundancy and backup, which again is becoming of some interest in the offshore applications. And then a new developing approach is contactless slip rings. That is growing in interest. With the perception is if you remove the sliding contacts, then you remove a number of the issues involved with a slip ring. That is a technology that we have as well. Okay, spend a few moments on the slip ring contact technologies. There are three primary contact technologies used in slip rings today. Probably the oldest technology, and one that is quite prevalent in pitch control slip rings, is shown there on the top of this graphic, and it's the composite brush contact technology. Composite brush is just that. It's a type of brush that you would see in a brush type motor on the alternators of your car, where that is a chunk of metal or graphite pressed material that runs in contact with the ring surface. A good effective technology for high power transmission. It is by definition a sacrificial technology, and what I mean by that is that it is a sizable piece of material, and it is intended over the life of the operation to wear away. And in doing so, it has some inherent issues dealing with wear debris that accumulates. It has to be cleaned, becomes a maintenance item as it begins to coat ring barriers and surfaces inside. You can have arcing issues, so few disadvantages with the composite brush design. A very popular technology, and one that we use very prevalently here at Moog Components, is monofilament alloy brush. As shown there in the in view of that technology, the typical design setup is a single wire, round wire brush that runs in a V-groove shape. This technology is one that we use in a lot of products, especially used where you need to have a very compact design, but it does require lubrication. You have to keep these contacts lubricated and to keep them operating and prevent the galling of the ring surfaces. That does become a maintenance item as things over time have to be cleaned and relubricated, but it is a very prevalently used technology. In Moog's pitch control designs, we use what's shown there in the bottom, and that is we call it a fiber brush design. It is a monofilament alloy wires, but it is a group of wires, sometimes usually between 10, 12, sometimes as many as 15 wires that go into a tube, and then those wire fibers then splay out across the ring surface. A very clean operating technology, no lubrication required, and a technology we've applied in virtually all of our pitch control slip ring designs. This slide shows a couple of different designs. The one on the left is a monofilament wire type of design, and as you can see, the rings there to the right utilize the wires in the V-grooves, but there are multiple wires and a wide ring with many V-grooves in it that would be used for power. And as you can see, over time in operation, the lubrication that's used on the rings kind of becomes a magnet and attracts and holds a lot of dirt and debris in contact with the ring. So as you can expect, over a period of time, you're going to have operational issues as that debris builds up, as it accumulates around the brushes and into the rings. And then, of course, at some point will have to be cleaned out and relubricated to keep adequate operation. Over on the right is a composite brush unit, and there in the circle you can see the accumulation of wear debris. Again, it is a maintenance item to remove covers, clean out wear debris from the barriers and inside the unit to keep these units performing. In each of these situations, the first thing that typically is going to happen is as you have an accumulation of this debris, you begin to impact your data handling circuits. Most often it is seen in the turbine operation as you start to bring out data signals. You begin to lose your control capabilities, and then eventually it can, of course, lead to a complete system shutdown. This is one of the Moog pitch control slip rings with fiber brush technology. This particular unit, at the time we took this photograph, had been operating out in the field for about 5 years. One of the unique features of the Moog fiber brush technology is that it does operate with a relatively low brush force in comparison with the monofilament or the composite technologies, which means it creates very little wear debris. The multiple brush fibers rest rather lightly on the rings, but yet have very good compliance and operation in shock environments. But that intimate contact against the ring surface and at a low brush force generates very little lubricity. And again, since it is a low brush force technology, there's no lubrication. So you can see after 5 years of operation, you can see some very light visible tracking shown on the rings. But again, it's still extremely clean after 5 years of turbine operation. One of the items you see as well in turbine operation is the power handling. As Nick mentioned in his presentation, a large majority of turbines operate in cold weather. Cold weather brings its own unique set of circumstances, and of course, as Nick pointed out, icing on the blades, but it also can cause some performance issues in the pitch control slip ring. That comes from the standpoint that as everything gets cold in the turbine operation, the bearings start to get very tight, get very cold. The lubrication in the bearings at the blades gets cold, and the system receives a command to pitch and move. You can see some pretty significant current draws as those servo motors kick into operation and make a move. Tie on to this the fact that you do have applications needs now for heaters, for batteries out in the cells, and you begin to really tax the power handling capability. That's one thing that we're very conscious of in our slip ring designs. This particular slip ring that we're showing the test data for here was one that operated at a nominal 65 amps. Our concern was, did the slip ring have the capability to be able to handle these high current draw situations? So we put the slip ring into a test where we slowly increased the current up to first the operating condition of 66 amps with no issues. Then we increased it above that up to a continuous operation at 88 amps. And then to really test out the capability of the design, we took it up to 130 amps, which is double the operational requirements. And we operated there for a period of 2 hours with no failure. So it's very important that the slip rings not only be designed, of course, for the application requirement as stated, but that there's significant margin in there for all the unexpected things that are known to happen in wind turbine operation. So our focus with Moog when we design our slip rings, and this pertains, of course, to the pitch control slip rings, but also to the majority of the other designs that we do as well, is that we're looking for how can we eliminate or reduce maintenance, and how can we make the product as reliable as possible in the application. With the fiber brush technology, we have achieved greater than 100 million revolutions with our operation of units in the field in a multitude of applications. No lubrication required. That means there's none of that accumulated debris around in the oil areas, no cleaning, no relubrication ever required in the design. The operating temperature, our standard operating ranges for slip rings that we design is down as minus 40 degrees centigrade up to plus 80 degrees centigrade. So we cover a very, very wide operational temperature area. So these things all come together to produce, a very high reliability design, and what in the end is lowers the life cycle cost. Certainly the intent with our approach to pitch control slip ring designs is to enhance the operation, keep the slip rings operating, and to keep the technicians from having to make nuisance trips up to clean brushes and do things just to keep slip rings in performance during the power generation season. So. And lastly, one of the things that we have learned over our years of involvement in the wind industry is the demands are not going to get easier. In fact, they're being taxed more and more as to the power requirements, the locations of installation, the heights. Everything is just getting more and more demanding, and you have to have the electrical contacts and the designs to keep up with that. The brush wear rates, that's what it comes down to in a slip ring. If you can provide a technology that gives you the longest possible life in the brush wear to meet the system reliability and life requirements, that's what the market is requiring. The elimination of maintenance, try to keep the technicians from having to climb the towers just to do slip ring maintenance. Keep the units operating, get a design that can be installed, let it run, let it be untouched. And the power, we are certainly seeing that power requirements are doing nothing but really increasing as far as the slip rings go. When you're getting into blade heating and again the larger systems, larger blades, more megawatt outputs, everything is increasing and getting more challenging with the current that's required. So we feel that Moog is we're highly capable in meeting this current and the next generation of turbine performance. Again, we're working on other approaches with our fiber brush technology. We have contactless power and data transfer capabilities, and of course with fiber optic, which gives you the immunity to EMI and other advantages, multiplexing of additional data across a single fiber. All of our various technologies coming together really put us we believe, in the forefront of providing high reliability and high performance pitch control slip rings. And with that, I thank you for your attention and appreciate again the opportunity to present Moog pitch slip rings.
Thank you very much, Steve, and to both of you guys, a job well done, and great pictures too, by the way. Ladies and gentlemen, here's a little contact information for you. And let's see, a couple questions that came to my mind. Steve, they're both for you. Was Moog's fiber brush technology developed specifically for wind turbine pitch slip rings?
No, Paul, as a matter of fact, it was not. We actually developed fiber brush contact technology back in the early 80s, and it was done initially for NASA. At that time, the satellite applications really suffered from two of the issues that face pitch control slip ring designs now, and that was the fact it was a monofilament wire. It had to be lubricated, and of course, a service called space is, if not unheard of, extremely expensive. And the other technology used was the composite brush. And again, wear, debris, outgassing from materials in the brushes cause problems there. So we actually started out with the fiber brush technology to solve an issue with space applications. Since that time, the fiber brush design has evolved its way into many of our military products, high-end products we do for the medical market, and then in about 1991, it found its way into our commercial industrial business. And if I may also say, that's one of the great things about my work here at Moog in the industrial arena is the fact that we get to take advantage of some very high-end developments that are used in the military market, and then eventually evolve those into being commercialized and into our commercial products. So that was the genesis for the fiber brush.
I see. And just one more question then. Why is the slip ring an important solution as turbines begin to age?
Well, there's tens of thousands of turbines installed in the world, and many of those date back quite a few years. The technologies that were used in the pitch control slip ring area, of course, were the technologies available back then. But again, all those the growth in the third-party service market and the maintenance of turbines that are already out of warranty or more coming out of warranty has really heightened the sensitivity and awareness for the need for better performing components in certain areas of the turbine, and we've seen that opportunity for the pitch control slip ring to be increasing dramatically. People are looking for bringing newer technologies in older turbine models, and it really has been a fast evolving area for us as we're working more and more with directly with wind site owners and operators, and we're being presented with opportunities and requests to, can you make this component better for us? And there's just keeping the turbine up and operating and enhancing the performance even on these older units is really a fast evolving area in the wind industry.
Excellent. All right, thank you very much, Steve. Nick, I have a couple questions for you. One has to do with calibration. How can the system be calibrated?
Yes, Paul, that's a very good question. The good thing about the detection system is that the calibration is automatic. Once the engineers have commissioned the system in the wind turbine and installed the sensors and connected it up and got everything communicating, the system will self-calibrate over a period of time. What it is essentially doing is, as the turbine is operational, it's measuring the mass of the blade, and it uses that number to look for changes. As the ice accretes on the blade, that mass obviously increases. So the calibration is inherent in that very process.
Excellent. Okay. My next question for you has to do with installation of the ice detection system. I can see how you'd install it on a brand new blade. I think you do that in the factory. But what about an existing turbine? Can you modify it, retrofit it with the ice detector?
Yes, Paul, we certainly can. In fact, that's a good question because, as you said, ideally we'd like to install the system in the factory. That's the right place to do it, the proper place to do it, because you have all the processes, you have the staff, the labor, all the materials and everything you need at hand. But it can be done in an operational turbine in the field. So we can go into, we have to lock the rotor in what we call rabbit's ears position, so that's one blade vertically down and two blades upwards, and that enables us to go into two of the blades at the same time. We go into the blade, and the thing about the ice detection system is that the sensors are mounted at the root of the blade, so you don't have to go very far into the blade, typically a meter and a half into the blade. The blade surface is then cleaned, the sensors are attached using special adhesives, and the cables run to the optical interrogator located in the hub. So yes, it's a relatively easy process. If we had many wind turbines to do it at numerous wind farms, and we were using the same operator, what we would normally do is to run a training program where we would go to the site and for the first couple of turbines maybe do the installations themselves whilst they were being observed by the operator staff. And then we would do a transition to the operator's team. And that shows that anybody, given a certain degree of training, can install these sensors in the field.
Mm-hmm. I see. Very good. Well, that's good news. That's good news for people with existing turbines. All right, ladies and gentlemen, that just about wraps things up here. I want to thank you very much. If you'd like to follow us through, you can do so on Twitter, Facebook, and LinkedIn. And you can discuss this on the Engineering Exchange at engineeringexchange.com. And that's it from the staff here at Wind Power Engineering. We wish you a good and productive day.